Okay, so hello everyone. Today we're gonna go with kinetics of a particle because we're already done with kinematics of a particle. And today we're gonna focus on the effects of force on the motion of particle or on the motion of a body. So just to recap, previously we discussed about the different types that a body can attain a different type of motion and the different types of coordinates from which these motions can be described. We also talk about the absolute and the relative motion and the uh, absolute dependent motion using ropes or any other constraining members. So it's all about kinematics, the geometry of motion. Today, what we're gonna deal with is the cause of those motion, the force that cause this motion. So let's start. Let's go with our outlines. What are we gonna learn from this topic? So these are the outlines. First, Newton's second law. Second, the equation of motion. The third, the equation of motion for a system of particles. Fourth, equations of motion using rectangular coordinates. Also, we're gonna deal with equations of motion using different coordinates such as the polar coordinates, the tangential and radial coordinates. Fifth, frictional forces, kinetic friction, static friction, and last is the summary of the procedure analysis for this type of engineering problems. Okay, so Newton's second law. What is Newton's second law? First, I think we have to define the word kinetics. Okay, kinetics. What is kinetics? Well, kinetics is a branch of dynamics that deals with the relationship of the change in motion. That deals with the change in motion of a body and the forces that cause this change. So kinetics is a branch of dynamics that deals with the relationship of the change in motion of a body or a particle and or between the forces that cause this change. And the basis for kinetics is, of course, none other than Newton's second law. Newton's second law, if you can recall, states that a body that is initially at rest or initially in straight line constant motion, right, will accelerate. So will accelerate. There are two options there. One is that a body that is initially at rest and a body that is initially in motion, which is provided that it is straight motion, straight constant motion, both will accelerate in proportional to the force applied and with the same direction of the force applied. That is the statement of the Newton's second law. This law can be verified experimentally by applying a force, a net or unbalanced force to a body. For example, there is a body, you have to apply a net unbalanced force and then it will accelerate. By measuring the force that you have applied and the acceleration that it receives, if you divide the force and the acceleration, it will result to a positive scalar m, which is called the mass of a body or the mass of an object. This is one way of verifying the Newton's second law. And the mass, as you can see, is a quantitative measure of the resistance of the particle to a change in its velocity. And sometimes it is referred to as inertia. The higher the mass, the higher the inertia. The lower the mass, the lower the inertia. And the inertia is a measure of the resistance of change. The first original formulation of Newton's second law is in this form, and that the one that is popular, which is this. So mathematically, we can express this, or we can rewrite this form into that popular notation or expression, which is F is equals to ma. This is called the equation of motion, and this is one of the most popular formulations in mechanics. Okay, so for most of speeds, for most of motions, this law works very well, but we know that according to other scientists, especially Albert Einstein, this has a limitation, because according to him, the speed, the motion, distance, and time, all of them are not absolute. Meaning that if an object is in very, very high speed, especially approaching to the speed of light, the experience or the phenomenon is quite or completely different. There is a phenomenon called length contraction and time dilation. So the law of Newton's second law breaks down at those speeds. But since we're only dealing with speeds that are not that high, or for most engineering problems, the speeds are not very, very fast. They are fast, but still very less than the speed of light. These effects can be neglected. For most engineering problems, the effects of theory of relativity are negligible. Alright?